1.5 is on the inverse of a matrix, and basically it's a square matrix, so it's usually n by n. So before we get into inverse matrices, let's talk about our to solve an equation. So suppose this is just a regular equation with real numbers. You're asked to solve ax equals b. Very simple. Way back pre-algebra type stuff. They wouldn't have been taught it like this, but this is basically what you are actually doing. So since excuse me, a is in the reals, there exists an inverse, a inverse in R, and that's called the multiplicative inverse. And what you end up doing then is multiply both sides of the equation by A inverse. And we all know that, right? So you multiply on both sides by A inverse. And so you start with AX equal to B. Again, all real stuff here. And then you multiply both sides by A inverse, like this, and then technically it's left-hand multiplication. And then since A inverse times A is equal to 1, you end up with 1 times x equal to A inverse B. A inverse, so the A inverse 1, that's the multiplicative identity. Not all systems, of course, have multiplicative identities. So if you were to stay in the natural numbers, you would not have or any rationals. Integers. You would not have multiplicative identities. You would not have multiplicative inverses. In the rationals, you do, of course. You have inverses. And so you would then 1 times x is just x. That's the multiplicative identity. Which gives you that, which gives you A inverse B. And then, of course, we can write that as B over A. So that's the technique you would use. Obviously, you don't, show all those steps right off the bat. But when you start breaking apart properties and rules, that's how you are showing it. So the question is, do matrices have multiplicative identities? Inverses and identities. So if you have AX equal to B as your matrix equation, do you have automatically A inverse? Okay, and that's the question, which you probably guess on that one, whether you do or not. So let's look at this then. For a system of equations with n unknowns, so x1 to xn unknowns, we express in a matrix form, as I did above. So we express the system, or like we may express it or can express it. We express the system in matrix form. So we did that. So this is our matrix form. Let's just put that here, right? Duplicate that. And that's called our matrix equation. So our matrix equation looks like that. And we want to develop ways to solve that. So basically, we want to talk about A inverse. So this whole section is really on that and what properties it has. So we're going to define Here's a definition of an inverse of a matrix. And it's usually inverse of a square matrix. For us, that's all we're going to end up with. There's other ways to define it in higher levels and stuff. I never actually seen it. It's a tangent type stuff of the main direction of what we do. So here we go. An n by n matrix is invertible, meaning an inverse exists, if there exists, let me say it like this, in an n by n matrix, A is invertible. Just throw in the matrix. Matrix A is invertible. So we're only talking about square matrices right now. If there exists a matrix B, which is n by n, such that, and then what you'd expect, A times B is equal to B times A, which equals the identity matrix of n by n. If you find a matrix B like that, then B is called the multiplicative inverse of A. So if that's true, the matrix B is called the multiplicative inverse of A. Same as above for real numbers. So if B does not exist for A, so if B does not exist, we all know D and E, for the matrix A, then A is called singular, or A, we just say is singular. So singular, non-singular has to do with that. Okay, so that's the definition of an inverse matrix. It's what you'd expect. Now we'll talk about some properties of matrices. This is the first theorem we come through that's of this stuff, theorem 1.9. This is on uniqueness. So, uniqueness of an inverse. Matrix. So uniqueness of an inverse matrix, this is a typical way we're going to show how to prove uniqueness. So it's not just about inverses, but just in general, how do you prove uniqueness? So there's only one. So uniqueness means, right, there's only one. All right, so this is what it says. If A is invertible, or is an invertible matrix, then its inverse is unique. Like there's not another one. So we can say then the inverse of A is A inverse. So it's not like A1 inverse or A2 inverse. You can just call it that. So the way you show uniqueness is this. So basically the general idea, before I write this up, is you assume there's two different matrices or of whatever. If you uniqueness in general, you assume there's two different things You call them X, Y, you call them A, B, and then you show, doing properties, that they must be equal. So it's like you're assuming there's more than one, so you just say 2, and then you do your operations, and in the end, you show they are equal. That's how you show uniqueness. That's the proof of how to show uniqueness. So to do this proof, we need to have a matrix that's invertible. So it says if A is an invertible matrix. So this is our hypothesis. So we need to stick with that and assume A is invertible before we can try to show any of the rest of this stuff. So we say first you say proof, then you say assume A is invertible. And then we're going to come up with, assume that two different matrices, we'll call them B and C, are inverses of A. Suppose both B and C are inverses of A. All right, so then we apply basically the properties of inverses, the definition. So we get, once you make the assumption that they are inverses, then we get all of this. And I like to highlight some of this stuff. It comes up against later. Except let me change my font size on my highlights. So here's the definition of an inverse matrix. So we get all this stuff basically right here, that the product's equal to I and all that. So what we can do is, is we have this. So then, by definition, we have A times B is equal to B times A, which equals to I. And we have the same thing for C, right? Because we're assuming they both are. So A times C is C times A, which is equal to I. So now we will show that B has to equal C. So there's different ways to maybe start this, but we're going to start this with A times B is equal to I. So let's multiply both sides by C. And so you get, and I'm going to go ahead and do this right here so I can fit everything there. So C times AB is equal to C times I. And then we can associate. So by associative property, we can associate that as C times A times B equal to, and then we could just say C right now, but I'll leave it as C times I. So the next step we'll say C times A is I, right? Because that is by our assumption. And then we have our identity as well. So we could say that is just going to be C times A is I because of above. So this is just I times B, which is C times I, the identity matrix. And then because I is the identity matrix, those are just equal to each other. So B equals C. Therefore, the inverses are unique. Okay, so therefore, the inverse is unique. Okay, so ponder this one, study that a bit, see if that makes sense to you. This is a typical one I would ask. Pretty much, if I ask you for a proof, you'll just be able to copy most of these. But this is one that's very doable in a regular situation as well, that I have you think about, memorize, whatever. But the concept, I think, is the most important thing here. When you're showing uniqueness, that's how you do it. You assume that there's two different things, whatever you're showing, that have the same property. And then you show those things must be equal. And then that means it's just one. It's just exactly one thing. Okay, I think we'll do a short video for that. That's pretty much what we have for the first property. Next will be kind of longer, just going into elementary matrices. Yeah, I think that's probably best. Okay.